For the extra practice, we're going to do a couple small examples, and then we're going to use the knowledge we've learned from this video to actually do some stuff with the Pythagorean theorem. For the first problem here, we have the square root of 40, and we need to find the largest possible perfect squares that can divide into 40. So I know that 40 can be divided by 2, but the largest possible perfect square that can divide evenly is actually 4. 4 times the root of 10. The square root of 4 is equal to 2, and the square root of 10 is going to just stay as the square root of 10. But remember that even though 10 can be simplified into the root of 5 times the root of 2, neither one of these numbers is a perfect square. Therefore, this is actually just fine for our answer. One more answer like this. Once again, this number can be divided by 2, but the largest possible perfect square is actually 16. Now, you could divide by 4 and then 4 again, but you would eventually get the same answer. I know that square root of 16 times the square root of 2 is equal to the square root of 32. Therefore, this number is equal to 4. This is going to stay as the square root of 2, and that is our simplest form. As we got to harder problems here, once again, we have to simplify the square root, but we also have the number that's sitting out front as well. So this has the largest possible perfect square as 9. 9 times 3 is equal to 27. So the square root of 9 times the square root of 3 is equal to 27. And the number 3 is still just floating out front. So this is going to stay as 3. This is going to change into the whole number of 3. And this is going to stay as the square root of 3. 3 times 3 is 9. Therefore, our answer is 9 times the square root of 3. Now, let's go to why are we learning how to simplify radicals? Because that's a good question. This is definitely not the most real-world skill that we learn in algebra, but there are times when it is incredibly helpful to be able to do this. And the most obvious time, and the reason why this was in this unit, is because it goes great with the Pythagorean theorem, which we hopefully remember. For any right triangle says that a squared plus b squared equals c squared, c being the hypotenuse or the longest side. So for this problem, we end up getting 64, or 8 squared, which is 64, 2 squared, which is 8, is equal to, 4, not 8. Where's my eraser? Need to get that off the screen. There we go. 4 is equal to x squared, which means that we have 68 is equal to x squared, or x equals the root of 68. Now, the problem is, if I type this into a calculator, it gives me a decimal, which means there's going to be some estimation involved, but sometimes I need the exact answer written in the irrational number form. And the best way to work with that would be in simplest form. So we can simplify the square root of 68 just like we've been simplifying everything else. The problem is maybe I can't figure out what numbers divide evenly, so I can cheat, and I know that it can be divided by 2. So I get the square root of 2 times the square root of 34. Then I also know that the square root of 34 can also be divided by 2, and gives me these 3 pieces left over. Square root of 2, square root of 2, and square root of 17. The problem is that none of these are perfect squares, but I notice, and I'm hoping we know from earlier sections, that square roots are the opposite of squaring. So the square root of 2 times the square root of 2 should be equal to 2. because the square root of 2 squared are opposite. Therefore, this is equal to 2 times the square root of 17, which means our x is equal to square root of 68, but it's also equal to 2 times the square root of 17. And these should be equal to each other. If I type this into a calculator and this into a calculator, I should get the same thing. Now, this is a tough section. I know it was super fun, and all of you are really excited to work on some examples. But if you need any help, make sure you come and talk to me. We can work through some together.